Hello, okay, so if you came from the last video, good for you. If you are starting off afresh and you have no idea what you're coming into, let me give you a quick, introduction. So today we'll be talking about alkenes and their reaction. In my previous video, we talked about, alkenes, physical properties, blah, 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 blah. But now we are talking about alkenes and their reactions. We're going to be looking at how to form alkenes, and we are going to be looking at how alkenes react and what are the products they can form. So first, we are going to focus on this aspect, okay? Now we shall look at the formation of alkenes. So how do you form alkenes? There are a few ways. The first way is, dehydration. Okay, so dehydration, what does that mean? Well, it just means that you remove water. You know how when you're dehydrated, you have a lack of water, right? So that's the same concept. Dehydration. So this, if you remove H2O, what does this mean? Let's think of a molecule that has the H and has the OH. What does that bring you to? Alcohols, right? Yes, you are right. So we are getting from an alcohol to an alkene, and because you remove this H2O, you would have a H2O too. So, what are the reagent and conditions? Excess concentrated H2SO4 or aluminium trioxide with heat, or H3PO4 with heat. So 3 conditions, that's a lot, right? Don't worry, just remember the first 2. Actually, excess concentrated H2SO4 is the most important one, so I would just suggest you focus on that the most. But in our syllabus, the first 2 are more important. So excess concentrated H2SO4 and hot Al2O3. So excess concentrated H2SO4. There's a whole setup. I don't really know if I should draw it, but the key idea is, okay, we have something like this, and then we heat it, and then there's a thermometer. Oh man, I should not be doing this. Okay, thermometer, and then it kind of connects here to sodium hydroxide, and you'll be confused, but like, why sodium hydroxide here? Well, I will explain that later. You kind of need to know that, so don't worry, it will be explained. Okay, let me try to do this. Oh, yes, okay, got it. So this is water. This is sodium hydroxide. This is, heat. This is that up here is a thermometer. Then this is your thermometer goes all the way, and this is the mixture of your alkene plus your acid. So this is the whole setup for the first reagent condition, okay? And there's something you need to note about this. They may ask you this during exam. So number 1, why do you need sodium hydroxide? So this is because if you use concentrated H2SO4, right, this concentrated H2SO4 may be reduced to sulfur dioxide during the reaction, and hence this acidic sulfuric gas is removed by bubbling the gas through the sodium hydroxide solution. And because you see here, okay, let me use a different color. Over here is the alkene plus the acid, right? So after the alkene and the acid undergoes dehydration, it would form the alkane plus some SO2 gas. So this alkane, sorry. Wait. Sorry. Hold on. I made a mistake here. This is alcohol. My bad. Okay, so the alcohol undergoes dehydration here, and it forms the alkene. And then the alkene gas and some SO2 gas would travel up here all the way down here, and then it gets bubbled through, and the SO2 gas the SO2 gas is removed by bubbling it through the NaOH, and when it comes up here, what remains is the alcohol gas, and then it goes all the way up, and when we are here, what's left is the alcohol gas. So that's the whole concept of how this works. My apologies for writing alkene there. I got myself confused too, not gonna lie. Okay, so that's the first concept for excess concentrated H2SO4 as a reagent condition. And now we look at hot Al2O3. Okay, let me just draw a rough one. Please do not copy this. This is a really bad drawing. Okay, and then this is heated up. We are gonna assume this is a Bunsen burner. Okay, so this is our rough setup here, and here are some porcelain chips. Wait, let me use a different color. Porcelain chips. Okay, and your porcelain chips, and here is your alcohol. Alcohol. And this alcohol is actually soaked in a mineral wool, but you don't really have to know that extent. So the whole idea here is this alcohol gets heated up through the porcelain chips. This porcelain chips is the hot Al2O3 because, you know, it's heated. It's heated, right? And then the alcohol becomes an alkene gas, goes through here, up here, is bubbled through, and our final product here is the alkene gas. So as this reaction goes on, right, the inside of the test tube will turn black as the reaction proceeds. Okay, I have run out of space, and let me use a different color. So the inside of the test tube turns black as the reaction proceeds. And why? Because this black thingy that appears is actually carbon. It's the carbon produced from the thermal decomposition of the alcohol. Okay, and a second thing to note is at the end of the reaction, right, the apparatus is left to cool with the delivery tube out of the water. And you may be wondering, which one is the delivery tube? This one, okay? That's the delivery tube. And this delivery tube is taken out of the water. Why? So as to prevent the water from being sucked back into the test tube. So why you want to prevent this? Because it's important to prevent this, as if you cool with this delivery tube in the water, right? As you cool down, then this air will contract here. Your air here contracts, and you know how it works, right? And then your water will go back in here, and that's it. Everything's ruined. So you need to remove it. Okay. So that is how, we get alkenes from alcohols. And a really important thing to note here would be Zizek's rule. But first, let's move on to another way you form alkenes. And the second way is, so the first way we have is alcohols to alkenes, and the second way is dehydrohalogenation of halogenoalkenes. So region and conditions: ethanolic potassium hydroxide with heat or heat under reflux. And this mechanism is known as elimination. Okay, basically, these two methods that we have gone through, dehydration and dehydrohalogenation, you can just write them as elimination actually in the exams. They are not very stringent on it. So, halogenoalkenes are those that have a halogen attached to, well, the end, right? It's just attached to the carbon chain. It can be anywhere, but so the whole idea here is to remove HX, to eliminate HX from the halogenoalkane, where X can be, so you eliminate HX, where X can be chlorine, bromine, or iodine. So the whole idea here is halogenoalkane, ethanolic KOH with heat, and then you form an alkene with your HX. So for example, we have, okay, and then upon undergoing elimination, you will form an alkene with HCl. And so you may be wondering, how do you derive what alkene product is formed, right? How do you know what alkene product is formed? Let's say we have, okay, how do you know whether this or this is formed? How do you know? Well, here's where we bring in a really important concept known as Zizek's rule. So in Zizek's rule, it states that For the elimination reaction of alcohols or halogenoalkenes to alkenes, the preferred product is the alkene with the greater number of alkyl groups attached to the doubly bonded carbon atoms. Okay, this sounds like a handful, right? But actually, it's quite a simple concept. So let's bring back this here. Right, if you're looking from this halogen alkene here, and we want to know the final product, so we're looking at these two products, right? And if we look back at Zizev's rule, it states that the preferred product is the alkene with the greater number of alkyl groups attached to the doubly bonded carbon atoms. So let's look at this one first. Okay, so this carbon atom has the doubly bonded carbon atom. You have one alkyl group here and you have one alkyl group attached to C here. So total you have 2. But for here, it's only 1 and the other carbon atom is bonded to 2 hydrogens. So total, you only have 1. And that's how you derive this to be the major product. This is the preferred product form. So, why is that the case? Because the more... Okay, why? Because the more substituted the alkene, and when we talk about substitution, in this case, we are talking about the number of electron donating alkyl groups attached to the doubly bonded carbon atom. So the more substituted alkene, meaning that the more electron donating alkyl groups attached to the doubly bonded carbon atom, the more stable the alkene. Because remember, alkenes, they are electron rich. So the more electron donating alkyl groups you have attached to it, the more electron rich the double carbon bond becomes. And that's how it becomes more stable. And that is why this is more preferred. So now we've gone through how alkenes are formed. Let's go through how alkenes react. So reactions of alkenes. So as we've talked about in the previous video, alkenes undergo electrophilic addition, right? I'm going to write EA as short here because it's a handful. Okay, so alkenes undergo electrophilic addition. And in this whole mechanism, there are 2 steps, okay? The first step is the addition of the electrophile. And the second step is the nucleophilic attack. And okay, so a few things to note about this mechanism. It may sound like a handful now, but it's actually not very complicated. So you add the electrophile and you have a nucleophilic attack. You don't actually have to write the name of the steps. You can just write as step 1, step 2. But a few things to note. This is the first step, this is the second step. few things. Okay, a few things to note about electrophilic addition. Number one, the first step is the slow step, because this involves the cleavage of the double bond. So this double bond is broken. And there's also the heterolytic fission of whatever you're adding to it. So it can be HX, it can be XX, and it can be OH bond. And because it's the slow step, this means that it has a higher activation energy. And also because it's the slow step, this also means that it is the rate determining step. So that's quite a few bit of stuff you can even know from the first step. And so now we further look into, before we even focus on the mechanism itself, we gotta understand how you form the products, okay? I know it's a bit different from how some people teach it, but this is just how I understand it. So when you form the products, right, how do you know like what on earth you are forming? And that is where Markovnikov's rule comes into place. Markovnikov's rule is quite a handful, just like Zizek's rule, but actually it's quite simple. There is Markovnikov's rule and there's a mechanism-based Markovnikov's rule, which I will be focusing on now. So what does mechanism-based Markovnikov's rule say? In an electrophilic addition reaction, the electrophile adds to an unsymmetrical alkene to produce a more stable carbon cation intermediate. So being formed faster in the slow step, the more stable carbon cation is more available to participate in the first step to form the major product. Now, this is a handful. I have to admit, it is a handful, and you at this point you might be very, very, very confused, and I can't fault you. It is very confusing. So let's break this down a bit, okay? Unsymmetrical alkene. Okay, unsymmetrical alkene. In this case, we are talking about alkenes that are, well, unsymmetrical. So some examples can be unsymmetrical. Unsymmetrical. Now, what are symmetrical alkenes? Symmetrical alkenes, see? Plane of symmetry. That's a symmetrical alkene. And these are unsymmetrical. And this is symmetrical. That's a rough idea. Carbon cation intermediate. What's that? We'll now look at that. Okay, so let's take a good example. What's a good example? Okay. So let's say we have CH3, CH3, H. This you can tell is unsymmetrical, right? Because about the CC bond, there is no plane of symmetry. So this is the first step. We have a partially negative bond and a partially positive bond here because bromine is more electronegative than hydrogen. So it pulls the electron pair closer to itself and hence it's partially negative. So in the first step, this CC bond is also broken, and here we add the electrophile, which is the partially positive hydrogen bond. Again, I'm not really going to go into specifics because I'm going to assume that you kind of know this already. This is more of a recap video. So this is a slow step. And now because you can form, right? So there are two different products that you can form. There are two different carbon cations that you can form because it is an unsymmetrical alkene. So here's the first product. First product that you can form would be second product. Where either one of the carbons of the CC double bond becomes a carbon cation intermediate, Br minus. And then fast undergoes the second step. So fast step. And over here, my bad. Then it joins and yes. And then you would form two different products. So okay. And if we look back at Markovnikov's rule, right? The more stable carbon cation intermediate. Remember previously when we talked about stability, we were talking about the number of electron donating alkyl groups attached to it. So the same concept applies here. So let's look at the two different carbon cation intermediates. This carbon cation intermediate has two electron donating alkyl groups attached to it. And this carbon cation intermediate has one electron donating alkyl group attached to it. So as such, we will note that this is more stable, right? So when it forms this product, then we can figure that this would be the major product, and conversely, this would be the minor product. So that's the whole idea of how you decipher which is the major product and which is the minor product. If you are wondering why is it that the more electron donating alkyl groups attached to the carbon cation intermediate makes a more stable carbon cation intermediate, this is because with more electron donating alkyl groups attached to the carbon cation intermediate, this disperses the positive charge on the carbon cation intermediate. So as such, it becomes more stable. So now we can finally focus on the main, like the whole idea of electrophilic addition, okay? So the first one is the electrophilic addition of HX to alkenes, where X here is ClBr. Okay, so reagent conditions. Dry HX, which is basically just a gas with room temperature. Mechanism. Electrophilic addition. So we will get a good example of, okay, I'm going to draw this plate formula just because it might be easier for some people to understand, but please try to draw structural formula for your exams because, please try to draw skeletal formula for exams because it is just way faster. So now we look at step 1. Okay, step 1 is the electrophilic addition of the partial positive charge of HBr. So okay, and then we have, this is partial negative, partial positive. Step 1 is EA of partial positive charge, so we add this. Conversely, heterolytic fission of this HBr bond. This is the slow step as we have previously mentioned, and as such we form. Note that this molecule is a symmetrical molecule, so it really doesn't matter which one you add it to. And Br minus. And then step 2 is the nucleophilic attack by the bromine ion. So we have our carbon cation intermediate, right? And then we have our bromine ion. And then it undergoes nucleophilic attack. And then this is the fast step because the first step is a slow step. And now we have formed our product. And this is our halogenal alkene. So this alkene becomes this alkene becomes a halogenal alkene. So alkene plus HX is halogenal. Okay. So note that because HX is polar, so that's why we have partial charges, okay? And if we were to talk about Markovnikov's rule here again, Markovnikov's rule states that when adding a hydrogen halide, aka HX, to the CC bond of an unsymmetrical alkene, the major product is the one in which the hydrogen atom of HX attaches itself to the doubly bonded carbon atom, already bonded to the greater number of hydrogen atoms. And if you realize, the concept is pretty much the same as Markovnikov's rule, which is mechanism based. There are a few exceptions to Markovnikov's rule though, so we'll talk about that later. Well, actually, you know what, we should talk about that now. The exceptions to Markovnikov's rule are quite simple. So, the first one would be the groups attached to the carbon cation intermediate. So if you have electron donating groups, this will make the carbon cation more stable, and hence you form major product. And if it's electron withdrawing, your carbon cation is less stable, so minor product. Second one is resonance second one is resonance stability. If your carbon cation intermediate undergoes resonance, for example, let's say it is next to a benzene ring, then this disperses the positive charge on the carbon cation intermediate, which then makes it more stable. So please note these exceptions, and if you identify them, they can override Markov's rule to form the major product. So now we come back to EA of HX. So we see over here, this carbon cation intermediate is sp2 hybridized, and hence it is trigonal planar with respect to the partial with the carbon cation intermediate. So this means that in the second step, the nucleophile, aka bromine ion, it can attack the carbon cation intermediate of the trigonal planar carbocation from either side with equal probability. And what does this mean? That means that in the final product, you form a racemic mixture, where a racemic mixture is one with equal concentrations of the two enantiomers. Okay, so that's EA of HX. Now let's move on to electrophilic addition of water. There are two methods, okay, namely the lab method and also the the lab method and my brain. Okay, but basically in essence there are two different methods, and I will be going through them one. Lab method and industrial method, my bad. But so for the lab method, in this case we are looking at how we add water, aka H and OH minus, to this CC bond of alkene. So first, for the EA of water, we would have reagent conditions. Number one, cold concentrated H2SO4, and number two, H2O with heat. Now you may be wondering, why do you need two different conditions in this sense? Isn't that just really confusing? Why do you need two different conditions, right? Well, that's because for this whole idea, it writes a bit differently. Okay, so let's further look into this. So step one, same thing, electrophilic addition. So I'm not going to draw a bunch of other stuff now. We'll keep it simple. Step one, we have the H2SO4. So we add the H2SO4. And then we form an alkyl hydrogen sulfate. That's a handful, right? Well, don't worry. The H is added here, the C, H, O, SO2, OH. And then our step two, step 2 is where we undergo hydrolysis. Now, that sounds a bit confusing, right? Don't worry, we will now show you. Okay, step 2 is, well, hydrolysis, and that's why we need H2O with heat. If you're wondering how we form this step 1, right, I'll explain it later, but first let's go into step 2. Okay. And then you add this H2O, and then where H2SO4 is regenerated because it is a catalyst. Okay, so if you're looking at this, right, you'll be like, huh, what on earth is going on? Well, you just have to remember this as is, but you may be tasked to drawing the mechanism for step 1. So how this mechanism for step 1 works is, number 1, you need to add the electrophile. It's the same concept as the rest, it's just there's a step 3 now here. Okay, so CC, and then there's a H O S O O H O. Okay, oops, I think I'm running out of space. Okay, and then you form slow step, then you form your carbon cation intermediate here, and together with so that's your first step. And then your second step is where you sorry for the mess, I know it's a bit messy, I did not plan this space properly. Okay, and then H, C, and this product is the same as this product here. So here is the rough idea of the electrophilic addition of water. And as I have mentioned, this is the lab method. So if we're looking at the industrial method, okay, industrial method, if we are looking at industrial method, the reagent and conditions would be H3PO4 on silica, high temperature and pressure. Okay, and so we don't really have to know much about this, but we just need to know that this is, well, also electrophilic addition. You don't have to draw the whole mechanism here because I think it's a bit complicated, so you don't have to. So now we go on. Okay, we move on. We've now looked at the EA of HX, EA of water, lab and industrial method. Now we are looking at the electrophilic addition of halogens. Okay, so the first one is halogens in CCl4. Note that X here, right? We are talking about Br2 and Cl2. Why is that the case? Because fluorine, right, it reacts explosively with alkenes, so it's not favorable. And iodine, the reaction is thermodynamically unfavorable because, well, it is all the way the bond is so strong that you would just need so much energy. So here, now we're looking at EA of halogen track, the reagent and conditions. X2 in CCl4, room temperature, dark, mechanism, electrophilic addition. And now we look at the steps. Okay, so and you're wondering why I thought this halogen is non-polar. Why is it that there's partial charges here? Well, because in this halogen, right, when it approaches this electron-rich CC bond, it then the electron cloud gets polarized as it approaches the electron-rich CC bond, and hence, you know, the side closer to the electron-rich side becomes partially positive and the other side becomes partially negative. So now we continue, slow step. Over here we are assuming that, you know, we are assuming here that we have a symmetrical alkene, okay? Then step 2. And that is your product. My bad. If in this case we are not looking at any specific one, then it would just be an X. Okay? And now EA of X, right? And so the first one would be in CCl4 and the second one would be in water. So over here, the halogen atom and the OH group are added across the CC bond. Okay, so reagent and conditions, dark, mechanism, same as everything else, electrophilic addition. Now we look at the first step. You add this electrophile, and this electrophile here is, well, okay, you know, we don't look at bromine, we just look at X in general. So X, partial positive, partial negative. With a bromine ion. And then step 2 is where the water comes in. Okay, so step 2 is where our water comes into play. Then you get the nucleophilic attack by the water. And this is the fast step. And note that this is an oxynium ion, but you don't really have to know. So why is it that in the second step, water is the one that attacks the carbon cation instead of the halogen ion. This is because the water, which is present in larger excess than the halide ion, acts as a competing nucleophile. And so this oxygen of water forms a bond with the carbon cation intermediate to form an oxynium ion. Okay. And then we have the step 3 because, well, this is not the product we want yet, right? So C. Then we lose the proton, okay? So this goes back here and it's the first step. Now, we have our final product. So now we have gone through all the electrophilic addition reactions. A very important one to note now is oxidation. We have mild and strong. So let me split this into 2. Okay. So we go mild and we have strong. Okay. For mild oxidation, reagent and conditions is KMnO4 with H2SO4 or NaOH. It really depends on whether you want it acidic or basic condition. Cold. Then the reaction is just mild oxidation. And so how this works, it's just that we you have a CC bond, right? And your product is one where you just add OH to it. So OH and OH. And what will be your observations is that because it undergoes oxidation, your purple KMnO4 decolorizes. And if you use NaOH, this means that you have basic condition, right? Then you would form a brown-black precipitate of MnO2. But note that this is only if you use NaOH, okay? And now we go on to strong oxidation. Reagent and conditions, KMnO4. Actually, note that strong oxidation and mild oxidation, right? Your reagent conditions are pretty much the same. The only difference is temperature. And that's how you differentiate between mild oxidation and strong oxidation. And because in strong oxidation, you need heat because your CC bond is completely broken, okay? So let's say your CC, right? And then it will be broken. It's broken. It forms an entirely new product. And your observations here is that, well, purple KMnO4 decolorizes. Same and then also MnO2, you know, the same if NaOH is used. And lastly, if it's a terminal alkene, you have CO2 form. Why is that the case? And also, how do you even identify what are your products formed in strong oxidation? Well, let me just teach you a really fast way, okay? Oh no, my line is not straight. Okay, so step 1, you break the CC bond. Okay, step 2, you add O to each carbon atom to form 3, replace H attached to C to form, you replace the H attached to C to form OH minus. Like you add a OH minus instead. Okay? And then 4, you check for further reactions. And 5, you check the medium. So this may sound a bit confusing, but let's break it down, okay? So for example, we have okay. So step 1, we cleave the CC bond. Okay, so then our products would be right? And then you add a O to each end. And because the C is O. And then you know the C is bonded, so you add a OH and a OH. And then, right? And then each one, you add a OH, you add a OH, you add a OH. Correct? And then you continue it down to see if there's any further reactions. So for this one, you have no further reaction. So your final product would just be like this. But this second product, what do you identify it as? This is ethanediol acid. So it further undergoes reaction to form CO2, 2 CO2 in fact. But this one, it is CO2, so 3 CO2. And that's your final product. And so now we've gone through oxidation, AA, everything, and now we go through the final few simple reactions of alkenes. So we have combustion, you know, same idea, you form CO2 and H2O, and lastly reduction. Well, you form alkenes. What are the reagent and conditions? Nickel, H2 gas, and heat. So for example, then H2. See? So you go from an alkene to an alkane. And that's all there is to know about alkenes. So for the reactions of alkenes, what we have looked at is how they form, Zizek's rule, reactions of alkenes, and how you form the major product depending on Markovnikov's rule, the electrophilic addition of hydrogen halides, the electrophilic addition of water, lab and industrial method, electrophilic addition of X2 in CCl4, X2 in water, oxidation in terms of strong and mild oxidation, how you derive the products, combustion and reduction. So thank you very much for being with me.